Good morning. Let me introduce myself. I am Dr. P. Ananthapadmanabhan, Associate Professor retired from Maharaj College, Ernakulam. Today I would like to take a most important technique, what we call infrared spectroscopy or vibrational spectroscopy, more precisely vibrational rotational spectroscopy. And what is the importance of this particular spectroscopy so far as the chemistry is concerned? It gives us an idea about bond angle, bond length, bond strength, as well as functional group of an organic compound. So, before introducing the theoretical aspect along with the applications of infrared spectroscopy, I would like to say something about the basics of spectroscopy. As you know, what do you mean by spectrum? Spectrum is nothing but photograph of an compound. How do we get a photograph? By interaction with electromagnetic radiation, what we call light. So spectroscopy is a technique which involves the interaction of electromagnetic radiation with the matter. As a result of this interaction, either electric component or magnetic component of electromagnetic radiation will be absorbed or emitted by the matter. How does it occur? When the energy or frequency of this electric component or magnetic component becomes equal to different energy levels present in a matter, their particular absorption or radiation will be absorbed and corresponding peak will be obtained in corresponding spectrum. And what do you mean by electromagnetic? Before going to details of this interaction, let me see some basics of electromagnetic radiation that you have already studied in your degree level. Electromagnetic radiation is the form of energy that can be radiated into space, which is associated with the electric component and magnetic component, which propagates in a perpendicular direction along the space. And there are two important properties of electromagnetic radiation. First property called particle property, which was proposed by Isaac Newton, known as father of physics, with which he could explain two important phenomena, reflection and refraction. But he was unable to explain diffraction and interference with this particle property, otherwise known as corpuscular property. In order to explain diffraction and interference, another scientist called Eugene Huygens proposed another property of the light, what we call wave property. So light has got two properties, particle as well as wave property, what we call dual nature. And dual nature of radiation was first proposed by Albert Einstein. Then coming to matter. Matter, as we know, made up of molecules, which is in turn made up of atoms. So energy of matter comprise energy of atom plus energy of molecule. And what are the contributions towards this energy? As you know, atom contains nucleus and electron. So atomic energy is nothing but sum of electronic energy and nuclear energy. When you take molecule, which may be monoatomic, diatomic or polyatomic, monoatomic, which contain only one atom, has got only one type of movement, what we call translation. What do you mean by translation? It is nothing but displacement of center of mass from one point to another, and the energy associated with this movement is called translational kinetic energy. Then if you take a diatomic, there are two types of motion in addition to translation. One is called rotation and other is called vibration. What do you mean by rotation? Rotation is nothing but change of orientations of atoms or positions of atoms in space without change of center of mass. And energy associated with this rotational motion is called rotational kinetic energy. And another is vibration, which involves the movement, the change of either bond length or bond angle without change of center of mass. The vibration movement in which bond length changes is called stretching vibration and bond angle changes is called bending vibration. So E total is nothing but energy of nuclear plus energy of electron plus energy of vibrational kinetic energy, rotational kinetic energy, translational kinetic energy. And if you look at the difference in energies of these 5 contributions, it is found out that the delta E change in electronic energy levels between two shells, what we call K shell and L shell simply, is of the order of 1000 to 10,000 joules per mole. If you compare EV, it is of the order of 1 to 100 kilojoules per mole. So this is kilojoules, not joules, kilojoules per mole. If you compare delta E of rotational, it is 0.01 to 1 kilojoule. And if you compare the energy difference between two nuclear levels, it is greater than that of electronic. If you compare the delta E, change in energies of translation level, it is less than 0.01 kilojoule. So, you can see that there is no discrete energy levels in translational. That means energy levels are continuous. So no need of excitation or absorption here. All energies are almost same. So no translational spectroscopy is possible. Coming to nuclear, if you look at the electromagnetic spectrum, as you know, it extends from radio frequency wave to cosmic rays. The highest wavelength region is radio waves, then comes microwaves, then comes infrared, then comes visible, then ultraviolet, then X-ray, gamma ray, cosmic rays. Here we are interested in 5 or 6 regions from radio frequency region to ultraviolet. And using these energies, you cannot excite a nuclear energy level transitions. So no nuclear spectroscopy is possible. So we are interested most probably in these 3 excitations: electronic excitation, vibrational excitation and rotational excitation. Since the most highest energy is required for electronic excitation from a K shell to L shell or from one shell to another shell, we require the highest frequency region in the electromagnetic radiation, that is nothing but UV and visible. So electronic excitation, since it is possible from UV and visible, electronic spectroscopy is otherwise called UV visible spectroscopy. Then coming to vibration, the next energy required is for vibrational excitation. Since next come after UV and visible is infrared. So infrared radiation is required for a vibrational excitation. That is why vibrational spectroscopy is also known as infrared spectroscopy. And third is rotational excitation. Next part is nothing but our microwave region, which is responsible for an rotational energy excitation. So rotational spectroscopy is also known as microwave spectroscopy. Other thing is, there is another region what we call radio frequency, that is responsible for nuclear flipping, which give rise to nuclear magnetic resonance spectroscopy. Then, which are the three, as you know, the result of this interaction of electromagnetic radiation with the matter is called spectrum. And we have seen what is electromagnetic radiation, what are the important properties. Then we also seen what is matter and what is the different contributions of energy towards the total energy of matter. Then the three important properties of spectrum are number one, position. What do you mean by position of spectrum? Position is nothing but, you can see the position of a line in the spectrum when you plot the spectrum. And how can you measure, how can you express the position of this spectrum? By using three parameters. One is called wavelength. As you know, wavelength is nothing but the distance between one crust and one trough of a wave, or distance between two neighboring crusts or two neighboring troughs, which is expressed either in micrometer or in nanometer or in Angstrom. We know 10 Angstrom is 1 nanometer, as you know, that is already not going to the details of the conversions. Then is called frequency. As you know, frequency is nothing but number of waves passing a point in 1 second, which is expressed in hertz, which is nothing but 1 cycle per second. Third is wave number, which is nothing but number of waves present in unit length, which is nothing but 1 by lambda, usually expressed as centimeter inverse 1. SI, even though SI unit is meter inverse 1, commonly we used centimeter inverse 1 even in SI system. Number two, second, the most important property is width of the spectral line. Width of the spectral line. Which are the three parameters, which are the three contributions which causes the broadening of the spectral line? Three important parameters which causes is collisional broadening. What do you mean by collisional broadening? Which is most important in liquids as well as gases, but the most important is in liquids. This is very simple. When, as you know, in liquids and gases, molecules are in random movement colliding with each other. Collision become more effective if intermolecular attraction is stronger, which is more important in liquids. When molecules collide with each other, the electronic energy levels of valence electron, what we call charged cloud of valence electron, gets perturbed. And this perturbed energy levels give rise to broadening, what we call collisional broadening. Second contribution is Doppler broadening. Doppler broadening. What do you mean by Doppler broadening? This effect of broadening arises due to random movement of molecules, which is more effective in gases. Let me introduce what is that. If a molecule is approaching the detector, which moves with a velocity u, when it approaches the detector, it gets a vibrational frequency which is greater than the incident frequency by a quantity nu dash. That is the frequency that the molecule of the C, when it approaches the detector, is equal to frequency of the radiation, which is, what is a u? U is the velocity of the moving molecule. If it moves away from the detector, it gets a frequency which is less than nu equal nu dash equal nu into 1 minus u by c. And if you look at the Doppler effect, nu dash minus nu, it is delta nu by nu equal to plus or minus u by c. And this broadening is called Doppler broadening, and delta nu is called Doppler shift. And from kinetic theory of gases, it is shown that the Doppler broadening is directly proportional to or equal to 2 by c into root kt log 2 by m. That shows delta nu is directly proportional to square root of T. What is T? Temperature, and small k, as you know, Boltzmann constant, and small m is the mass of the molecule, and small c is the velocity of the light. And since Doppler broadening is directly proportional to square root of temperature, this Doppler broadening can be reduced by taking the gas samples at very low temperatures. And third property of the spectrum is what is called, the most important property of the spectrum is called intensity. If a particular spectral line is not intense, the corresponding spectroscopist cannot observe that. So the most important property of a spectral line is intensity, which depends on three factors. One is called transition probability. What do you call transition probability? It is nothing but the probability of transition of a system from one energy state to another energy state, which is governed by quantum mechanics by a set of rules, what we call selection rules. Second contribution towards intensity is population of states. What do you mean by population of states? Which is nothing but number of particles present in a given energy state that can directly absorb the radiation. If the population of the states, population in a particular energy state is very high, then the higher number of particles will absorb the radiation and will be excited to the higher energy state. As a result, intensity of the line will be very high. And this population of the state is generally given by Boltzmann factor, which is equal to, this is the formula, as you know, you might have studied all these things, where n1 is the number of particles in the first excited state, and n0 is the number of particles in the lowest energy state, what we call ground state. Delta is the energy difference between these two states, K is the Boltzmann factor. Generally, at room temperature, it is found that most of the molecules are in the ground state. So, the higher intensity will be observed when the particle gets excited from the ground state to excited state. Third contribution is nothing but line intensity. Third is called path length and concentration of the solution. As the path length is nothing but the length of the medium through which light passes, and concentration is the amount of the substance present in that given solution. Greater the path length and concentration of the solution, greater will be the light absorbed and greater will be the intensity, which is governed by an important law that you already studied, what you call Beer-Lambert law, which is nothing but absorbance equal to epsilon, which is called molar absorptivity or molar restriction coefficient, C concentration of the solution, and L what we call path length or optical length. that is A directly proportional to C as well as L. And another is, as we know, absorbance is related to transmittance by the relation minus log T. These are the three important contributions which contributes towards intensity. And before discussing this, I would like to say something about that I have forgot in the previous case, what is called line broadening. There are three, I have mentioned three factors. One is called collision broadening, second is called Doppler broadening, third is one more thing, the most important other thing that contributes towards broadening of the spectral line is nothing but natural line width, what we call lifetime broadening. What do you mean by lifetime broadening? This is very important in electronic as well as microwave spectroscopy. As we know, from Heisenberg's uncertainty principle, you might have, I don't know whether you have studied this uncertainty principle, delta E into delta T greater than or equal to h by 4 pi, where delta E is the uncertainty in energy of a molecule in a particular energy state, and delta T is the uncertainty in lifetime. As we know, since most stable state is the ground state, most of the molecules are present in the ground state. So uncertainty in time is very large. In that case, uncertainty in energy or uncertainty in frequency, as we know, delta E is related to uncertain frequency by the relation h nu, which is nothing but c by lambda, which is nothing but hc nu bar. Since uncertainty in energy is zero, uncertainty in frequency is also very small. In that case, we get a narrow or line, a sharp line. But when the molecule goes to excited state, where the lifetime is very small, here the delta T is very small. As a result, the delta E, uncertainty in energy or uncertainty in frequency, is also very large, which give rise to a range of frequencies rather than a single frequency, which also contributes towards what we call broadening of the lines. These are, so let me briefly discuss. The three important factors are, one is position, number two, position is measured by frequency, wave number and wavelength. Number two, broadening. Three factors which contributes towards broadening is collision broadening, Doppler broadening and natural line or lifetime broadening. Third important is what we call intensity, which is contributed by three important parameters: transition probability, which is given by selection rules, population of the state given by Boltzmann factor. Third is what we call path length and constellation, which is given by Beer-Lambert law. So, when you take a spectrum of an atom, similarly spectrum of a molecule, what is the fundamental difference between these two? As we know, the spectrum of an atom gives a sharp line because it involves only electronic excitation. But in the case of molecule, along with electronic excitation, which requires the highest amount of energy, simultaneously vibrational and rotational excitation will also occur. Each excitation will absorb on radiation, which gives an additional light. As a result, atomic spectra gives a narrow band spectrum, whereas in the case of molecular spectra, we get a broad spectrum. Then, how can you plot a spectrum? You can plot a spectrum by either absorbance versus wavelength, which gives a maxima, and either percentage transmittance versus wave number, which gives minima. Usually in IR spectrum that we are going to see is usually used percentage transmittance against wave number. This is something about the basics of spectroscopy. Then we shall pass on to the most important spectroscopy of today's lecture, that is infrared spectroscopy, as I have mentioned, vibration spectroscopy or vibrational rotation spectroscopy. You get pure vibration spectroscopy only in solid phase where rotation is completely prevented or hindered. So if you want to get pure vibration spectroscopy, you have to take the sample in pure solid state. Then, what are the and what is the important target of today's topic? We know when you compare the experimental findings of any spectroscopy, you have to give a correct explanation for that experimental observations. There comes the help of theoretical chemistry. So, let me see. If I take spectrum of a diatomic molecule, before that, as I have mentioned, we are going to use IR region for this. When we use IR region for this, we know there are three IR regions, what we call near IR, which is very close to visible, which extends from 12,500 to 4,000 centimeter inverse 1. Then middle IR, which is 4,000 to 667 or nearly, sometimes it is 500 centimeter inverse 1. Far IR, which is near microwave region, that extends from 5 to 50 to 667 centimeter inverse 1. Here, since most of the vibrations lies in the middle IR region, for our purpose, for experimental purpose, we usually use middle IR region for taking IR spectrum. Next is, what is the important selection rule? Classically, what is the important selection rule for a molecule to be IR active? Important condition is that there should be changing dipole moment. That is very important. Dipole moment change. There should be changing dipole moment during a vibration. As we know, there are two types of diatomic molecule. One is called homonuclear diatomic molecule, like H2, O2, Cl2, etc., which have no permanent dipole moment. They are non-polar molecule. They are always IR inactive. But heteronuclear diatomic molecule like HCl, carbon monoxide, etc., which have permanent dipole moment, is always IR active. And polyatomic non-polar molecule like carbon dioxide, some stretching vibrations give rise to changing dipole moment. So some of the vibrations of carbon dioxide is IR active, but water, which is a non-polar polyatomic molecule, have permanent dipole moment. So all vibration give rise to changing dipole moment. So all vibrations of water molecule is IR active. This is something about the introduction of IR spectrum. And coming to our point, which is the best model for a diatomic molecule, where I am coming to a theoretical aspect of IR spectrum. When I take let me take the basics of the formation of a diatomic molecule. Suppose I want to see the formation of hydrogen chloride. Let me take hydrogen, keep at the rest. Chlorine is at infinity. At this stage of infinite distance of separation, there is no interaction between hydrogen and chlorine. So both are highly unstable atomic state. In that case, they have high energy. When they are at infinite distance, there is no interaction. They remains as atomic state, which is highly unstable state. As a result, the energy of the system is very high, which is arbitrarily taken as zero. When chlorine approaches towards hydrogen atom, there are two types of interaction: nucleus-electron attraction as well as electron-electron or nuclear-nuclear repulsion will come into the scene. Since initially the electron-nucleus attraction predominates over electron-electron or nuclear-nuclear repulsion, stability of the system increases. As a result, the energy of the system decreases. Stability increases, energy decreases. At a particular point, this energy is nothing but potential energy because you are changing the position of the chlorine atom. At a particular distance, these two forces, attraction force and molecular repulsive force, becomes equal. At this equilibrium distance, what we call bond length, these two forces becomes equal. System becomes highly stable. At this stage, potential energy is minimum. If you squeeze the two atoms further, as you know, again the repulsive force predominates, and as a result, system becomes unstable, bond may break. So let me come to our point. So hydrogen chloride, generally a diatomic molecule, can be considered as a simple harmonic oscillator. Diatomic molecule can be, the first model is called diatomic molecule is simple harmonic oscillator model. What do you mean by that? Suppose I take the HCl from its stable state. If I stretch this hydrogen and chlorine from its equilibrium positions, as we know, the system will become unstable because energy of the system increases. So what is the tendency? As we know, there is a tendency, there is a force acting in a direction opposite to this displacement from its equilibrium position to bring back this particular two atoms to its stable equilibrium position. So if I stretch it, the retarding force will be in this direction, reforming force, it will be in this direction. If I compress it, again repulsive force predominate, again there is a reforming force which is in the opposite direction. That shows the reforming force will be always directly proportional to the displacement x, which is in a direction opposite to that of displacement. From its x can be taken as r minus req. This notation I have taken from Banwell. I take this class based on molecular spectroscopy by C.N. Banwell. R minus req. Since displacement and force, retarding force is directly proportional, but the direction is opposite, or if is equal to minus kx, this is nothing but important law. We know Hooke's law. Any movement that obeys Hooke's law is called simple harmonic oscillator model. So our in the simple sense, our diatomic molecule is considered as simple harmonic oscillator model which obeys Hooke's law, that is F equal to minus kx, where the force and displacements are in the opposite direction. And what is k? K is nothing but force constant of this simple harmonic. I shall give a simple example. If I take a spring and if I take two masses here, if I choose these two masses here, the force will be in this direction. If this is the displacement, if this is the displacement, the force will be in this direction. So these two masses connected by a spring obey simple harmonic oscillator motion. So our diatomic molecule simply considered as this simple harmonic oscillator model. And what is the potential energy for that? It is nothing but simple parabolic. That is, if I take energy versus x, this give you like this. And what is the selection? Well, if I put this potential energy in Schrodinger equation, we get energy of the vibrating molecule EV. I shall give you what is V. V plus half H nu oscillator. What is V? V is nothing but vibrational quantum number which can take value 0, 1, 2, 3, etc. And H is the Planck's constant. And nu oscillator is the frequency of oscillating molecule which is given by 1 by 2 pi root of k by mu. What is k? K is the force constant. What is mu? Mu is called reduced mass, which is equal to mass of the M1, M2 divided by M1 plus M2, where M1 and M2 are the masses of two atoms. So the frequency of the oscillator, here the frequency of our diatomic molecule depends on three factors. One is called mass of the atoms. Number 2, force constant or strength of the bond. As K value increases, force of the strength of the bond increases, and I have taken a simple value for a single bond. Single bond K is 5 into 10 raised to 5 dynes per centimeter. I have taken the CGS system. This is for single bond. For a double bond, it is 2 times 5 into 10 raised to 5 dynes per centimeter. For a triple bond, this is equal to 3 into 5 into 10 raised to 5 dynes per centimeter. So, K value gives the relative, the magnitude of what you call strength of the bond, means the reduced mass. So, the oscillator frequency depends on number 1, mass of the system, mass of the atoms of the molecule. Number 2, the force constant or strength of the bond. Third is arrangement of atoms within the molecule. So these are the three factors which usually contribute towards oscillator frequency. That is, one is mass of the atoms, second is force constant or strength of the bond, third is what you call arrangement of atoms in the molecule. And here the energy is given by joules. The energy is given the unit of joules. But we know in common IR spectrum, generally energy is expressed in terms of centimeter inverse 1. When centimeter inverse 1 is nu bar is nothing but E by Hc. So then nu bar become, or E V become in terms of nu bar V plus half nu bar oscillator, where nu bar oscillator is nothing but 1 by 2 pi c root of k by mu. Only I have divided this by h. And what is the selection rule for a simple harmonic oscillator? That is nothing but delta V equal to change in vibrational quantum number is equal to either plus 1 or minus 1. What do you mean by plus 1? Plus shows absorption, minus shows emission. And if I plot the spectrum For this transition of neighboring energy levels, we can see that all energy levels are equally spaced. What do you mean by equally spaced? In that case, if I take delta E, V to V plus 1, we get only one frequency. You can prove that. Time being, I am not going to details of that. And you can prove that by substituting in this expression. And that shows that, so you can show that this expression by substituting in this one. Okay. Now, if this is the case where we have, this is the simple harmonic oscillator model, and I shall give you one more thing which is actually against our classical mechanics, because if I substitute V equal to 0 in this particular energy expression, we can see that half nu bar oscillator. That shows even at the lowest vibrational energy level, the molecule can oscillate with a energy which is equal to half nu bar oscillator, and actually this energy is known as 0 point energy of the harmonic oscillator. This is the first model of diatomic molecule. But when we take the real spectrum, so according to simple harmonic oscillator model, since all energy levels are equally spaced, we expect only one absorption, because we require only one radiation, one frequency is required for all excitations of energy levels, because our selection rule permits that. Only that particular transition. But in real practice, when you take the spectrum of the real molecule, it is observed that more than one line, what we call addition lines, and in spectroscopic terms we will call it as overtones, combinations, differences, etc. are observed in the spectrum, in the real spectrum. In order to explain this, a sign is called PM modes. We know if I plot the real energy expression, potential energy against intermolecular distance, actually I have mentioned that at infinite distance energy is almost zero. As it approaches, energy decreases. At a particular distance, what we call bond length or equilibrium distance, where these two, attraction and repulsion, becomes equal, the potential energy becomes minimum, and then again increases. And if you compare the simple harmonic oscillator, this region and this region matches only up to small compressions and small extensions. Beyond that, after this, after a particular distance, in reality, a molecule will break. This breaking of the bond is not taken into consideration when we discuss simple harmonic oscillator model for a diatomic molecule. In reality, since the molecule breaks, PM modes proposed a new potential, what we call Morse potential, which can fit into this graph, which is nothing but V of x equal to the bond dissociation energy dEq 1 minus e raised to minus a x squared, where x is the displacement, a is a constant, dEq is the bond dissociation energy, and this, what do you call, this model is called anharmonic oscillator model. Anharmonic oscillator model for a diatomic molecule. And what is the selection rule for this? The selection rule is delta V equal to plus or minus 1. We will come to this later. Plus or minus 2, plus or minus 3. In a simple harmonic oscillator model, it was only delta V equal to plus or minus 1. Since we get additional bands, what we call overtones or a combination, the other selection rule has to be considered. If I look at the energy of this particular anharmonic oscillator, it is C EV equal to V plus half mu E minus XC into V plus half squared mu E. And an addition tape has come. What is XC? XC is called unharmonicity constant, and for small and actually for bonding stretching vibrations, XC is found to be very small, whose value is 0.01, very small. So for our practical purpose we can omit that term, but in reality that will come to the actual, that has got some contributions. And this is the energy of a anharmonic oscillator which permits this. As we know, as the value of V increases, since it is a negative minus sign, V increases, the energy levels becomes more and more crowded. That is actually happening near the breaking of the bond. The energy levels becomes continuum, and after this, if you again stretch it, the bond will break. So this energy of an anharmonic oscillator exactly fit into the diatomic molecule. But when you compare the energy of, and if I take this V plus half mu E is common, 1 minus XC V plus half, and earlier we have seen for a simple harmonic oscillator EV equal to V plus half new oscillator. So if you compare this, new oscillator equal to nu E 1 minus XC V plus half. So in the new anharmonic oscillator model, which is equal to nu E if V equal to 0. XC, the contribution of XC can be neglected. But as we know, if you fit this equation into the real molecule, diatomic molecule, we get the 3 additional bands, what we call overtones. Let us see how it is possible. Suppose I have seen that the delta V is plus or minus 1, plus or minus 2, plus or minus 3, etc. If plus or minus 1, 2 possibilities are there, either 0 to 1 or 1 to 2. 0 to, that is, it can be either V equal to 1 to V equal to 2. Here V equal to 1 to V equal to 3. But it is by Boltzmann factor at room temperature of 300 Kelvin. At room temperature of 300 Kelvin, it is observed that the population at V equal to 1 is nearly 1% of ground state population. Only 1% of ground state population. That means if I take any excitation from the first excited vibrational energy level V equal to 1, the intensity is very small. So that contribution cannot be taken into account. So we take only 3 V equal to 0 to 1, V equal to 0 to V equal to 1, V equal to 0 to V equal to 2, V equal to 0 to V equal to 3. We take only these 3. If I take V equal to 0 to V equal to 1, the energy, delta energy, we can calculate is 3 plus half new oscillator into 1 minus 2x. We take 3 vibrations, 3 energy levels, V equal to 0 to V equal to 1, V equal to 0 to V equal to 2, V equal to 0 to V equal to 3, because by Boltzmann factor we have seen that the population and the V equal to 1 is very small, only 1% of ground state population. So the change in energy for V equal to 0 to 1 equal nu bar oscillator into 1 minus 2 xc so much centimeter inverse 1. V equal to 0 to 2 delta EV equal to nu oscillator 2 nu oscillator equal 1 minus 3 xc, and V equal to 0 to V equal to 3 delta EV equal to 3 nu bar oscillator 1 minus 4 xc centimeter inverse 1. And since xc is very small, as we have seen 0.0 equal to 0.01, this is nothing but V equal to 0 to V equal to 1 appears at nu bar oscillator, and this is called fundamental frequency band, simply fundamental band. V equal to 0 to V equal to 2 appears at 2 nu oscillator. This is called first overtone. And V equal to 0 to V equal to 3 appears at 3 nu oscillator, what we call second overtone. So by this model, anharmonic oscillator model, we could explain the appearance of first overtone and second overtone and so on. And here you can see that the frequency of first overtone is greater than that of fundamental vibration, and second overtone in turn is greater than that of first overtone, but the intensity is highest for fundamental, then comes first overtone, then comes second overtone. That shows as we move from fundamental to overtones, even though frequency of absorption increases, the intensity of the spectral line gradually decreases. And there is a particular band in our IR spectrum, what we call hot band. What do you mean by hot band? It is seen that nearly if I take 600 Kelvin, if I increase the temperature, the population at V equal to 1 becomes appreciable. As a result, the transition from V equal to 1 to V equal to 2, which obeys delta V equal to plus 1, where delta E equal nu bar oscillator into 1 minus 4 xc centimeter inverse 1. That means an additional band will appear at high temperature. And how can you check whether it is a band at this band, what you call hot band? How can we check whether it is a hot band? Simple. Because if you increase the temperature, if the intensity of particular spectrum increases, that shows the appearance of hot band. So we have seen number one, fundamental vibration, number two, overtones, then hot bands. But we know when you take the spectrum, additional bands also appear. Which are the additional bands? P, Q, R, etc. branches appear in IR spectrum. In order to explain these additional branches, a third model of atom, diatomic molecule, was proposed. This is nothing but diatomic vibrating rigid rotator model. Vibrating rotator model. This is the model. Why it is possible? Because as we know, if I take rotational energy levels, the range is only 1 to 10 centimeter inverse 1. But if I take vibrational energy levels, it is of the order of 1000 centimeter inverse 1. That means, since the energy difference between these two levels are very large, it is possible to vibrate and rotate a particular molecule independently. And as a result, there is an important approximation, what we call Born-Oppenheimer approximation. You can see that Oppenheimer approximation. You can prove that the total energy not only depends on vibrational quantum number, it also depends on rotational quantum number J, which is equal to B into J plus and V plus half. We know mu oscillator minus V plus half square, mu oscillator and Xc. Oh, sorry, not harmonic oscillator model. Nu E Xc. So what is B? B is rotational constant. Rotational constant that we usually used in microwave, which is equal to h by 8 pi squared Ic, where I is the moment of inertia, which is equal to pi IR squared, mu r squared. Moment of inertia, mu r squared. From this you can see the bond length. J is the rotational quantum number, which can take value 0, 1, 2, etc. And which is the selection rule for this? The selection rule for this is delta J equal to either 0 plus or minus 1. Delta J 0 simply no rotation, and delta V equal to plus or minus 1 plus or minus 2 like that. This is the third model by which you can explain the three branches. How can we explain that branches? We know delta E is mu 0, what you call 2bm. This m is the change in rotational quantum number, which can be plus 1 or minus 1. And mu 0, what is called band center. This is, and if I substitute this delta J 0 corresponds to Q branch, you can prove that. Delta J plus 1 corresponds to P branch, R branch, and minus 1 corresponds to P branch. So by this diatomic rotator vibrating model, the scientists could explain the additional branches PQR. So we have started from simple harmonic model by which you can explain the fundamental absorption. Then By anharmonic oscillator model, we could explain the additional bands like overtones, and from this diatomic rotating vibrator model or vibrating rotator model, we can explain the PQR branch. And still there are other, this is not the latest, but it is there, but time being I am trying to restrict my discussion regarding the models here. And coming to polyatomic molecule. Polyatomic molecule. We know. Polyatomic molecule. We know. We are going to calculate number of vibrational degrees of freedom. Number of vibrational degrees of freedom. What do you mean by degrees of freedom? Degrees of freedom is nothing but the minimum number of coordinates required to locate the position of a particular atom in space. Number of coordinates required to locate the position of an atom in space. Since we require 3 coordinates x, y, z for each atom to locate in space, we know for one atom there are 3 degrees of freedom. 3 degrees of freedom. For if there are n atoms in the molecule, there are 3 n degrees of freedom. And we know how many there are 3 type of movement I have mentioned. Translation, which is nothing but displacement of center of mass from one point to another point, which is possible along 3 directions, x, y, z. So for each atom there are 3 translational degrees of freedom. And we know what is rotation. Rotation is nothing but without change of center of mass, there should be change in positions or orientations of atoms in space. As in, if I take a diatomic molecule without change in center of mass, if I take a linear molecule, I can rotate the molecule along the bond axis like this, or along the perpendicular like this, along the perpendicular like this. These are the 3. Either this, or along the bond axis. So, we take 3 vibrations, 3 energy levels, V equal to 0 to V equal to 1, V equal to 0 to V equal to 2, V equal to 0 to V equal to 3, because by Boltzmann factor we have seen that the population and the V equal to 1 is very small, only 1% of a ground state population. So the change in energy for V equal to 0 to 1 equal nu bar oscillator into 1 minus 2 xc so much centimeter inverse 1. V equal to 0 to 2 delta EV equal to nu oscillator 2 nu oscillator equal 1 minus 3 xc, and V equal to 0 to V equal to 3 delta EV equal to 3 nu bar oscillator 1 minus 4 xc centimeter inverse 1. And since xc is very small, as we have seen 0.0 equal to 0.01, this is nothing but V equal to 0 to V equal to 1 appears at nu bar oscillator, and this is called fundamental frequency band, simply fundamental band. V equal to 0 to V equal to 2 appears at 2 nu oscillator. This is called first overtone. And V equal to 0 to V equal to 3 appears at 3 nu oscillator, what we call second overtone. So by this model, anharmonic oscillator model, we could explain the appearance of first overtone and second overtone and so on. And here you can see that the frequency of first overtone is greater than that of fundamental vibration, and second overtone in turn is greater than that of first overtone, but the intensity is highest for fundamental, then comes first overtone, then comes second overtone. That shows as we move from fundamental to overtones, even though frequency of absorption increases, the intensity of the spectral line gradually decreases. And there is a particular band in our IR spectrum, what we call hot band. What do you mean by hot band? It is seen that nearly if I take 600 Kelvin, if I increase the temperature, the population at V equal to 1 becomes appreciable. As a result, the transition from V equal to 1 to V equal to 2, which obeys delta V equal to plus 1, where delta E equal nu bar oscillator into 1 minus 4 XC centimeter inverse 1. That means an additional band will appear at high temperature. And how can you check whether it is a band at this band, what you call hot band? How can we check whether it is a hot band? Simple. Because if you increase the temperature, if the intensity of particular spectrum increases, that shows the appearance of hot band. So we have seen number 1 fundamental vibration, number 2 overtones, then hot bands. But we know when you take the spectrum, additional bands also appear. Which are the additional bands? P, Q, R, etc. branches appear in IR spectrum. In order to explain these additional branches, a third model of atom, diatomic molecule, was proposed. This is nothing but diatomic vibrating rigid rotator model. Vibrating rotator model. This is the model. Why it is possible? Because as we know, if I take rotational energy levels, the range is only 1 to 10 centimeter inverse 1. But if I take vibrational energy levels, it is of the order of 1000 centimeter inverse 1. That means, since the energy difference between these two levels are very large, it is possible to vibrate and rotate a particular molecule independently. And as a result, there is an important approximation, what we call Born-Oppenheimer approximation. You can see that Oppenheimer approximation. You can prove that the total energy not only depends on vibrational quantum number, it also depends on rotational quantum number J, which is equal to B into J plus and V plus half. We know nu oscillator minus V plus half square nu oscillator and XC. Not harmonic oscillator model. Nu E XC. So what is B? B is rotational constant. Rotational constant that we usually use in microwave, which is equal to h by 8 pi squared IC, where I is the moment of inertia, which is equal to pi IR square, mu R square. Moment of inertia, mu R square. From this you can see the ground length. J is the rotational quantum number, which can take value 0, 1, 2, etc. And which is the selection rule for this? The selection rule for this is delta J equal to either 0 plus or minus 1. Delta J 0 simply no rotation, and delta V equal to plus or minus 1 plus or minus 2 like that. This is the third model by which you can explain the three branches. How can we explain that branches? We know delta E is mu 0, what you call 2bm. This m is the change in rotational quantum number, which can be plus 1 or minus 1. And mu 0, what is called band center. This is, and if I substitute this delta J 0 corresponds to Q branch, you can prove that. Delta J plus 1 corresponds to P branch, R branch, and minus 1 corresponds to P branch. So by this diatomic rotator vibrating model, the scientist could explain the additional branches PQR. So we have started from simple harmonic model by which you can explain the fundamental absorption. Then by anharmonic oscillator model we could explain the additional bands like overtones, and from this diatomic rotating vibrator model or vibrating rotator model we can explain the PQR branch. And still there are other, this is not the latest, but it is the, but time being I am trying to restrict my discussion regarding the models here.